Hi students, in this first video for online lecture 5, we are now going to talk about the basic fundamentals of a not so basic and fundamental idea, and that is quantum mechanics. So what is quantum mechanics? First off, we have to make a fairly big and bold assumption, and that is that all particles can act as a particle or as a wave. So let's look at the energy quantized by an electron. De Broglie reasoned that an electron obviously has mass, but if we get it going fast enough, it will actually observe a wave-like behavior. So he came up with these two equations saying 2 pi r equals Rn, principal quantum number, times our wavelength. So then he did some assumptions and came up with what is known as the de Broglie wave equation. That is equal to Rh over mu. You're probably asking yourself, what are h and mu? Well, h is obviously our Planck's constant. But remember, Planck's constant was using the ideas of energy and waves. So really, the numerator is treating this as a wave part of our duality. As I look at the bottom of my fraction, you will now see that u is the velocity of our particle, in this case, the electron, and then finally, m is going to be the mass of our particle. So now, as you can see on the bottom, I have mass times velocity, and this is now looking at the particle side of our duality and treating it as our momentum. Remember that mass times velocity is our momentum. So let's look at the example that you see here over on the right side. If in example 1, I drop a stone into the water, you will see upon its impact, here in example 2, a small droplet of water having the identical mass. This is using the ideas of classic ideas of for every action there is a reaction. So you're going to have that water be very similar to the mass of the stone coming in because of the attempt of displacement. But where the quantum mechanical side comes in is using the ideas of waves. So once that stone hits the water, not only will we try to displace the mass, but then we are going to see some energy go and be spread throughout the media in the ripple of the waves. This is incredibly important because we are now seeing mass turn into energy. This is going to be a very important thing when we see some of our quantum mechanical ideas. The easiest way to look at this duality is the slower a particle travels, whether that particle is, say, a car, a person, a small bug, or then an electron, it's going to act more like a particle, which we typically deem classical or Newtonian physics. The faster it travels, it acts more and more like a wave. So as you have probably seen, electrons, because they move towards the speed of light, will actually start to act more like a wave, even though they have mass. If we get a very fast car, it will start to look and adopt some wave-like properties as it were increasing towards the speed of light. Now, some of you may not believe in all of this, but if you can think of stuff like the Flash, the superhero, the faster he goes, they have gone and accentuated the fact that he is going to have wave-like properties, and that is why you see the stream of light coming out from him. So what does this mean to us as actual fundamental scientists? This means that everything in the world has a wavelength. It's just a matter of, can we see that wavelength? So let's try a couple of examples. The first one is the fastest tennis serve is about 150 miles per hour or 68 meters per second. Calculate the wavelength associated with this tennis ball traveling at that speed. So now we're taking a tennis ball being hit by a racket, which may not seem as a very fast motion in the world of science, but as you can see, 150 miles per hour is normally a little too much to handle for most professional tennis players. So let's see what this means. So what I'm going to do is now look at my de Broglie wavelength equation. So I will have my h over my m u. You are more than welcome to use v in this case. U is just nice because of having all of the different variables that we've had for v in our kinetic energy, as well as having our symbolization for our frequency. So because I have my H, we have had that value many a times. That's 6.63 times 10 to the minus 34th joules times seconds. Then I have my denominator, which I need my mass to always be in kilograms. This is because the joule is actually the kilogram meter squared per second squared. So every time you deal with any type of conversion going from a mass to a velocity or energy, you need to have our kilograms. So in this case, I am going to have 6.0 times 10 to the minus 2 kilograms. And I need my velocity, which is going to be 68 meters per second. So now I have to calculate all of this in a calculator, and using correct sig figs, I will get a value of 1.63 times 10 to the minus 34th meters. Now you're probably wondering, what does that mean? Well, now we must look at the cross-section and dimensions of our species. A tennis ball has a fairly decent size, that of a few centimeters in a diameter. But look at how small this wavelength really is. This means that our particle, comparative to our de Broglie wavelength, the particle is going to be much more dominant. It has a much more noticeable wavelength to size ratio. So this means that if my wavelength starts to approach the dimensions of the particles that I am going to deal with, that means it is going to adopt wave-like properties. So now that I've calculated this wavelength, we can say, even though Andy Roddick hit very, very fast tennis balls, it is still acting like classical Newtonian physics. So let's go ahead and look at B. Calculate the wavelength associated with an electron moving at the same speed of that tennis ball. So now let us go and determine our de Broglie wavelength. So we have our H over mu. So that is once again going to have our 6.63 times 10 to the minus 34th joules times seconds. Our mass this time is not going to be the mass of a tennis ball, but the mass of an electron. So this will be 9.1094 times 10 to the minus 31st. Once again, we must have kilograms. And then finally, we need to have our 68 meters per second. So now that we have done this, we can put this into the calculator, and we would get a value of 1.07 times 10 to the minus 5th meters. So now you will notice that I have a much larger wavelength than what I did for my tennis ball. That is coming because of the mass of the electron being so small, but because we are going very close to the actual dimensions of our electrons when we're talking about the radius, this would be considered quantum mechanics. This means that our electrons are going to act more like a wave because of their properties. So let's try this example. A student has decided to accelerate a proton, given a mass, on the hopes that it will reach a velocity of 121,000 meters per second. In what range will this proton emit radiation? So you'll now see that I give you 5 possibilities, but now we can look at a particle going and emitting radiation based off of it being accelerated. So let us go and use our de Broglie wavelength equation one more time. So we have our h over mu. So now I need my h, which was that 6.63 times 10 to the minus 34th joules times seconds. Now I need to look at the mass. And as you can see, there is a difference in this mass in the problem. I have grams. We must convert this to our kilograms. So if you get a problem like this, make sure that you always double check your mass. So the fact that we have a mass of 1.67 times 10 to the minus 24th grams, we need to divide that by 1,000, and we will get 1.67 times 10 to the minus 27th kilograms. Always, always check this. So now I will then take the velocity of 121,000 meters per second, and I will now determine a de Broglie wavelength of 3.28 times 10 to the minus 12th. So now you will see that the range that this proton will emit radiation based off of the possible choices is going to be letter E. So it's very important that you see that as we are starting to accelerate certain particles, especially those of electrons, if we get them going fast enough, they will stop acting like a particle and thus will become a wave. The second important quantum mechanical idea is the idea of the uncertainty principle. So Werner Heisenberg, who was a very famous German scientist during World War II, came up with the idea that there is a fundamental limitation to just knowing how precise you can have both the position and the momentum of a particle at a given time. So as we look at his equation, you will see this delta x. This is the uncertainty in the position. Then we will also have the possibility and uncertainty in our momentum. So notice that you can have mass and velocity. So it's very important for you to know that as an electron is being sped up, because its velocity is going to have some certainty, then its position becomes uncertain. Then as we start to determine its position, then we are going to be uncertain of its velocity. This is all based and done off of the ideas of, once again, either one of these species having a greater value than that of Planck's constant over 4 pi. So you're probably wondering why Walter White is on my slides. Well, for those of you that watch Breaking Bad, one of Walter White's drug names was Heisenberg. This is because as the police were starting to chase him, he was always one step ahead. When they were certain of his position, he was 2 steps ahead. As they were getting closer, they were actually farther away. So even in our mainstream media, such as great TV shows like Breaking Bad, we are going to use these scientific terms to discuss the ideas of uncertainty. So when dealing with Werner Heisenberg's idea of the uncertainty principle, the more you think you are certain of the position, you must give up certainty on the velocity. If you are more certain of the velocity, you must then give up certainty in its position. This duality really goes hand in hand with the ideas of the particle-wave duality. So let's look at a little bit of math in order to see the importance of our ideas of the uncertainty principle. So let us look at an electron moving at a speed at 8.0 times 10 to the 6 meters per second. If the uncertainty of this measurement is 1%, calculate the uncertainty of the electron's position. I then give you the mass of the electron. So first things first, for A, we need to have some basic ideas of understanding of our math. So what I can say is that our change in velocity, which is our uncertainty, is going to be equal to our 1%, so that's 0.010, times our recorded velocity. So that is going to be 8.0 times 10 to the 6th meters per second. And if I do that math, you will end up getting 8.0 times 10 to the 4th meters per second. So this now has the uncertainty listed in the velocity. So what I can do is take that velocity, multiply it by the mass, and now get our uncertainty in the momentum. So in order to do that, I can have my uncertainty in my momentum, our delta P, be equal to my mass times our velocity uncertainty term. So if I do that, I now have a mass of an electron that is going to be 9.109 times 10 to the minus 31st kilograms. And now we must multiply that by our uncertainty velocity. So that is going to be 8.0 times 10 to the 4th meters per second. So now we have the uncertainty in our momentum. If I do that, you will get a value of 7.3 times 10 to the minus 26 kilograms times meters per second. So we now have the uncertainty in our momentum. But that's not what we want. We want to know the uncertainty in the electron's position. So what we can do here is now go back to our expression and say our unknown in our position, or our uncertainty, is equal to our h over 4 pi. And now we could put our momentum term on the bottom of our fraction. Remember, our delta P was on the left side, and I'm just merely dividing by it. So now I can state that we have 6.63 times 10 to the minus 34th joules times seconds. We will divide that by our 4 pi, and we will also divide that by our momentum term, which is 7.3 times 10 to the minus 26 kilograms times meters. Now, there's a lot of unit conversion in here, and I will tell you that the remaining unit that you will get is meters. So you will now get 7.2 times 10 to the minus 10th meters. So this means that as that electron is traveling, this is the uncertainty that we have in an area. So this means that if I have an electron in a position, 7.2 times 10 to the minus 10th in either direction, that electron has a possibility of being there. So let's go and try with something that seems to be a little bit more useful for us to have. Let's use a baseball. Hitting a baseball, being thrown at 100 miles an hour, would make you a professional baseball player. And even the best professional baseball players only hit the ball really 1 out of 3 times. This is because if we throw the baseball hard enough, it may start to act like a wave. So let's see if there is a great amount of uncertainty when dealing with our baseball. So if I do this, I can look at the uncertainty of its position by having my delta x. I can put that equal to my pi over 4 pi and our momentum. So now we know that our h is 6.63 times 10 to the minus 34th joules times seconds. And then as we're doing this, we are going to have our 4 pi. And now we need to put in both momentum terms. So that is going to be our idea of momentum, which is going to be not only the uncertainty of our momentum, which is the term I'm putting in now, our 1.0 times 10 to the minus 7th, but as well as the momentum of my 6.7 kilograms times meters per second. So if I do this, I will now get an uncertainty in its position of 7.9 times 10 to the minus 29th meters. How much of a difference is that when you really think of the dimensions of a baseball? It's really not that big. But as we start to throw that baseball faster and faster and faster, we would start to get it to act more like a wave, increasing its uncertainty. The last thing we want to discuss in this video is the Schrödinger equation. Schrödinger's ideas started in 1926, and he wrote an equation that described both the particle and wave nature of an electron. He called these wave functions. This is done by the Greek letter psi, and as you go further into chemistry, you are going to see these wave functions. These can be handled by very difficult calculus when trying to solve for possibly the velocity or the mass or particle nature of a wave. But we aren't going to deal with that. We are going to deal with the assumptions that come from a wave function. First thing that describes is the energy that the electron has with a given psi. This energy should coincide with the principal quantum numbers that Bohr discussed back in the original ideas of his equations. Finally, if you take the square of the Greek letter psi, you're actually going to find the probability of finding an electron in a volume of space. We are now going to consider that our orbitals. So Schrödinger's equation can only be solved exactly for one atom, that being the hydrogen atom. This is important because there is only one electron in that atom. What happens is that you must approximate for multi-electron systems. If you go on into further chemistries and take what is known as physical chemistry, actually solving for this equation for hydrogen will take you a pretty good lecture of about 35 to 40 minutes. Trying it for helium, which is a 2-electron species, will take you the better part of a couple lectures. So the important part of Schrödinger's equations are he's taking the math and now bringing the ideas together of both the particle and the wave. So Schrödinger is now giving us some mathematical and quantifiable basis that the electron can act both as a wave and as a particle. In the next lecture, you are going to see how we are going to use these ideas of the 3 experiments that you've seen in this video to help give us the picture of where electrons should be. Have a great day.